So we'll start with what information is given to us that from the text that is going to be important for solving this problem. Weight W, which actually will also be in the free body diagram, but I'll include it here too. It's supporting a weight of 1,000 newtons. A lot of this other stuff is going to be in our diagram anyway, so we'll just wait for the free body diagram for that part. And we want to know, what are we asked to find? Well, we need to know the forces in all three of these things. But the naming convention I'm going to use, I'm going to continue throughout the whole problem. There's two rods, so each of them can carry a force that could be in tension or compression. So I'm going to name things that are forces that can hold tension or compression. I usually will use F as that name, and then the points at which it passes through. So there'll be a force in the rod that goes from A to D. Also, there's a rod from A to B. And then there's a cable that holds this together that goes from A to C. But the cable or the rope can only hold a tension. So usually my notation for that I use is going to be T. And that makes later our kind of a quick check a little bit easier to make. So the tension AC, we want to know these three forces, one of which we know is in tension. Two of them can be in compression or in tension. That's ultimately what we need to find. Right, so now we need the free body diagram. The first thing we need to do is choose a point of interest that we're going to draw. What are the forces that act on that point? So in this case, what point of interest would make sense to choose if we're interested in these three forces? Right, point A, because it's connected to the two rods and is connected to the cable, and then there's this applied force on it as well. So A makes sense to choose. And for particle equilibrium, this is often obvious, but not always. I'm going to use the coordinate system that was given to us, this right-handed coordinate system. So we have this origin over here. So point A, because we're in 3D, I'm going to be using unit vectors. I'm going to be putting coordinates of these important points down. So for point A, to go from the origin to point A, I have to go 2 meters in the x direction. I then have to go 6 meters in the y, and it's in the xy plane, so 0 in the z. So that's my point A. I have a rod going from A to D, so I'm going to need to know point D so that I'll be able to find the direction that points from A to D later. So point D I'm going to mark here and put its coordinates. It's on the y-axis, so it's 0 in the x. I have to go 6 in the y and 0 in the z. I have a rod that goes from A to B, so I'm going to put the coordinate of B down here. That's on the x-axis. I have to go 2 in the x, 0 in the y, and 0 in the z. And I have a cable that goes from A to C. So I want to know the point C, which lies on the z-axis. So that's going to be 0, 0, 3. So those are just putting down the important coordinates I'm going to need to use, because I can use these directions now because I know the direction of these three forces. There's a force, I'm assuming tension, that goes from A to B, which I've already named FAB. There's a force in the rod that goes from A towards D, again assuming tension. I've already given that name FAD. And there's a force in a rope or a cable from A to C, which I've already named TAC. All the arrows come out from the point, so they are indicating that my assumption is tension here. Because they're all pointing, starting at the point A and pointing towards D or towards C or towards B, and not the opposite. And then I have one more force acting on point A, and that's going to be that weight force it's holding, which we were told is 1,000 newtons. So in my free body diagram, I have my point of interest A, my right-handed coordinate system with the origin over here, all of the forces that act on A labeled with either these unknown values or this known value of 1,000, and I have all the dimensions. In this case, my dimensions are in the form of coordinates. They're going to be crucial for my next step. So I'm going to use this for my equation step. Before I get to writing equilibrium equations, I find it easiest to start writing any of the unit vectors I'm going to need, and that makes the equilibrium equation step, or the equilibrium equations, easier to write. So any force that's going in a direction that's not along a axis, I'm going to need to find the unit vector of. And for this case, I will also write out explicitly all of the unit vectors I need. So let's start with U hat AB. So in what direction do I have to head to go from A towards B? So one method we can use is we can use the end point B minus the start point at A and then normalize it. But this actually lies along the y-axis, actually in the negative y direction, so I don't actually have to go through that step. What will its unit vector be if it's pointing in the negative y direction only? Just negative j hat. It's a unit vector, right, so its magnitude is 1. So if it's pointing in the negative y direction only, it's as simple as negative j. So if I look at the direction from A to D, what is that unit vector going to be?
Negative I hat.
Right? It's pointing in the negative x direction to go from A towards D. So since it's only in the x direction, it's just negative I. Again, I can go through these steps again later, there too. So the one I do have to do some work for is the unit vector that points from A towards C, because that's not along a coordinate direction. It's not only in I, J, or K. So here I do have to go through the longer form. I have to take the end point C minus the start point A. So it's going to be 0 minus 2I, 0 minus 6J, and 3 minus 0, K. And then divide it through by its magnitude. So in this case, that is going to have a magnitude of 7. So 4 plus 36 plus 3 is 49. Square root is 7. So I can write this as nicely as a fraction. And then that 1,000 newtons is acting only in the negative z direction, so that'll just be in the negative k. We'll get to that once we write our equations. All right, so again, I started out by writing my unit vectors. Now the next step is going to be fairly easy. I'll explain the premise of what I'm doing, but in the future I'm not going to go through the kind of explicit steps I'm taking. So what I can do, for example, if I want to write that's TAC, remember from that previous slide, I can write that as its magnitude, which I don't know, times its direction. So I can write this as negative 2/7 magnitude TAC I hat minus 6/7 TAC j hat plus 3/7 TAC k hat. Where I'm going to be using this idea is if I only need to know how much is in the x direction, I'm just going to be pulling off that coefficient. If I want to know just what part of it is in the y direction, I'm pulling out that coefficient, and just the part in the z direction is just going to be that coefficient. And that's true for any of my forces, because I'm going to be writing these equations as scalar values. So I'm not putting in i's, j's, and k's. I'm just putting in the coefficients that would be in front of their I, their j, and their k term. So I write my first equilibrium equation. I'll start with x. I want to know what are all the components of forces that act along the x direction. Now I can look up here at my unit vectors and just pull off what would the coefficients be in front of the I hat terms.
Negative 180.
Right, well, so starting at TAB here, this only has a j component, so TAB would not have anything in the x direction. if we look at AD, it has a -1 times the magnitude, which I don't know, is going to be TAD. And then finally, for the tension AC, again, these are being driven by this picture here, but these unit vectors are telling us what components of it are in each direction. For TAC, we know that -2/7 of it is in the x direction because of that part of its unit vector. And then none of the 1,000 is in the x direction. So my first equation, -TAD minus 2/7 TAC, those are all the forces with all the components of forces that lie in the x direction. I do the same thing for components that have y in the y direction. So now TAB has a j component, and its coefficient is -1, so -1 FAB. AD does not have a j component, so it will not be in this equation. And the tension in AC has a j component, so that will be -6/7 times TAC. Again, the weight is only in the z direction, so it is also not in this equation. Looking at my equations so far, I have 3 unknowns, but only 2 equations. So I can't solve anything for numbers yet, so I'll come back once I write my 3rd equation. Now I get my 3rd equilibrium equation. I have forces that act in the z direction. This has nothing in the k. AD has nothing in the k. AC is going to be 3/7 times its magnitude in the k direction. Now I look at my free body diagram, and remember I have that weight force of 1,000 newtons that's acting in the -k direction. So now in equation 3, this is where that 1,000 newtons is going to be counted, is in the z direction, because that's the only direction in which that weight force is acting. Now looking at these 3 equilibrium equations I wrote, there's a total of 3 unique unknowns to them. So at least TAC, TAB, FAB, FAD. So at this step, I at least know I have a solvable system of equations. I have 3 equations, which we presume are unique, and 3 unknowns. So then in the solve step is where I can actually do that. This one is easy to solve by hand. If I start at equation 3, the only unknown I have is TAC. So I can move the 1,000 to the other side, multiply by 7/3, and I can get that TAC is going to be 2,333 newtons. Since I have a number for TAC, if now I look at equation 1, TAC I know its numerical value, so the only remaining unknown will be FAD. So I can put that answer into equation 1 and solve for FAD. FAD, I get a -667 newtons. Looking at equation 2, again, I know AC. I don't know AB. So I can take that answer for TAC and find my last remaining unknown, FAB. And I get FAB is -2,000 newtons. My answers aren't quite done yet, because anytime I have something that can be in tension or in compression, I have to make sure that I interpret my result. Because, at least the way I present it, I'm always assuming tension. I'm always assuming it's pointing away from the object and not towards it. That means that my assumption is that I'm assuming tension, so a positive result will mean my assumption was correct. It is indeed in tension. Whereas a negative result will mean my assumption was the opposite, and it's actually in compression. So it's okay as we let the math tell us if that assumption was right or wrong. The numbers are consistent with our picture, are consistent with our equations. That's the important part. Now at the interpretation step, the tension in AC, or the TAC, is positive, which means it is indeed in tension, which I want to indicate. This will also act as a quick check, if this were a negative value, something went wrong. The rope cannot push, it can only pull, it can only hold tension. The force in that member AD is negative, which is okay, because that rod can be in compression or in tension. The negative indicated my assumption was incorrect. It's actually in compression. And AB, also negative, means that my assumption was wrong. It too is in compression. So my answer I would report is the numerical value and my interpretation was in tension or was in compression.